with some check your understanding questions of Chapter 10, projectile motion. Oh, hello, welcome. You've had a chance to think about the two-dimensional motion more, and we'll see how you're doing. While you're logging in, and I'm stalling on the first one, today we will finish most of special theory of relativity on Chapter 35, which means we've done 4 more chapters since the last exam, and they form a unit, so we will have an exam on them. Wednesday we will review chapters 6 and 7. 6 was on momentum and impulse. 7 was on energy. Chapter 10 on projectile motion. And Chapter 35 on special theory of relativity. And then your exam will be Friday. Yeah. Just a sec. Right. Well, I'll look that up later. I'm remembering that your homework was for 7 and 10, because we finished that last week. 35 we'll finish this week, today. So since we have an exam on Friday, the homework won't be due on the weekend like it normally is. It'll be due before Friday. The due date is in WebAssign. I just can't remember right now off the top of my head. Did I make it Wednesday? Did I make it Wednesday before class or midnight? I was thinking I did it at night. So you'll have a couple more days on that after we finish it. But realize that the homework for Chapter 35 will be due before our test Friday, hence Wednesday. But you've had a chance to be working on that anyway. We started it last week. It was available last week. So that's what I wanted to get straight. Okay. 10, 9, 8, 7, 6, 5, 4, 3. I guess there's just less of us today. 2, 1. 2/3 of us A, but some of you B. All right. I am going to give you a clue and reopen it. So a cannonball is fired horizontally at 10 meters per second. So its horizontal speed is? Does that change? Oh, yeah, only if a force acts on it. Inertia would keep it at 10. What happens, though, once it's fired? There is an acceleration due to gravity, which will give it a vertical velocity. How fast will it be going after 1 second vertically? What's the acceleration due to gravity? 10 meters per second squared. So in 1 second, it'll change its velocity by 10 meters per second. So after 1 second, it'll be going 10 meters a second vertically. So you got 10 meters per second horizontally and 10 meters per second vertically. I've reopened it. Talk to your neighbors. See if that changes your answer or not. So basically, yeah, you got 10 meters per second that way. And after 1 second, you have 10 meters per second that way. Two things are happening at the same time. Maybe you could relate it to us shooting projectiles from over here. If you give it 10 meters per second up, at the same time you give it 10 meters per second over, you know which way it goes, don't you? It's kind of like, what's the projectile's initial speed? Or here, what is its final after a second? So all speeds and velocities have two components. One might happen to be 0, but not necessarily. We break them into components to think about them. But they're both there. It got quieter, so I guess I should start counting again. 10, 9, 8. Oh, still don't know, huh? I'll even draw a picture. It's got 10 meters per second one way, 10 meters per second other. So what is its speed? Its speed 1 second after being fired. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Oh, wow, you guys shifted. A lot more of you are on B. It was bigger on A before. You guys are confused. Isn't this fun? This is good. What's the resultant speed here? Point. What direction would the resultant speed be? Right, that way. How long should I draw it? You just add those two vectors. It's going to end up over there, the direction. So, you know, it's the position, it's going like that. It's a parabola. And after 1 second, we're over here. It's gone 10 meters per second that way. It's now 10 meters per second this way. And so it has 10 this way. It has 10 that way. Right at that point, its instantaneous velocity is in that direction. The speed is its magnitude. Is that vector longer or shorter than these? Longer. So it's not A. It's not 10 meters per second. It's 10 meters per second horizontally. It's 10 meters per second vertically. But combined, its speed at that point is more than 10. Because you got it pushing in two directions. How would you find its actual length? Pythagorean theorem. It comes out to be 14. The other answers were like 20. Well, it's clearly not twice as long if you can just visualize the components. The tough one is whether it's 14 or 16 if you're not actually calculating it out. You betcha. I'm happy to. So this is a right triangle. And if you need reviews, again, it's in your book. Here's a right triangle. This side is 10 meters per second, so 10 squared. Plus this side, the length of that, the magnitude of that is 10. That equals the hypotenuse squared. That's Pythagorean theorem. A squared plus B squared equals C squared. This is 100. That's 100. It's 200 squared. So H is the square root of 200, which is way closer to 14 than any of the others. When it's a 45-degree angle, this is actually 10 times the square root of 2 more, which is 1.4. 10 times 1.4, 14. Does that help? Conceptually, I just wanted you to at least realize it had to be more than 10. But it's not doubled because they're not in the same direction. They don't just completely add to each other. That would be if they were both in the same direction. You'd have 10 from one and 10 from another. The result would be 20. They're not in different directions, different components. So it's bigger than 10, but less than 20. Questions remaining? So again, my emphasis here is that we try to think about how far it's going horizontally by just dealing with its horizontal velocity, and vice versa, vertical. We actually use that. 1 second. How fast is it going after 1 second? This is a stepwise problem. There's more than just one thing you have to think about. Again, that being the acceleration due to gravity is 10 meters per second squared, so after 1 second it's now going 10 meters per second. Vertically. But overall, the bullet, the cannonball, is going to be going 14 meters per second at that point. 10 horizontally, 10 vertically. Try this one then. The idea here being the plane's going yay fast relative to the ground. If you have the wind helping you, you can add that speed to it. And it seems like it's going even faster relative to the ground. But if the wind's coming against you, it subtracts from your speed. It's going to slow you down relative to the ground. But that's when you're in the same direction.
You're saying the wind's hitting it exactly right.
This one, what if the wind, the airplane's coming one direction and the wind is hitting you perpendicular at a 90-degree angle? That's what a crosswind is. It's not with you or against you. It's beside you, coming in at you at perpendicular, at a normal. So again, your clue is your plane has a certain velocity forward. The wind gives it a velocity perpendicular to it. So again, you have two components. I guess it's this way, but it's going to cause a resultant. You're adding those vectors just like we did here. Well, it doesn't matter for the answer to this question whether it stays on its course or not. But yeah, planes are usually want to go, like I'm trying to get from Kansas City to St. Louis. So it tries to maintain its direction, and it'll compensate for crosswinds.
Would this still apply to if there's like an updraft?
Yeah, if there was an updraft, well, there's yet another force with a third velocity that you would add to it. We'll just stick.
One's on the x-axis, one's on the z-axis.
Yeah, it can be three-dimensional. Absolutely. We're just not going to go there we'll keep the waters a little clearer for you folks. But you're absolutely right. This stuff all applies in 3 dimensions as well. You would just have components in 3 directions. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Most of you say it increases. That's right. It's a different application of the same problem. Think of this as the speed of the plane going 10 meters per second relative to the ground. We see it going 10 meters per second. But then there's a crosswind blowing, trying to move it this way at 10 meters per second. It's like this is looking from above now, if you will. Plane's trying to go that way. The wind's blowing this way. The result is those two together are making the plane go this way, relative to the ground. So yeah, it increases. This is added velocity to the plane relative to the ground. So it has to be something bigger if it's a crosswind. If the wind was this way at 10 meters per second, what would be its speed relative to the ground? Faster. And how much faster? Using these numbers. If the plane's going 10 relative to the ground, and you have the wind behind you blowing you forward at 10 meters per second, you'll be going 20. And if the wind's blowing this way, yeah, relative to the ground, you wouldn't be moving. The plane would be propelling forward, but the wind would be halting them. Watch this. Let's do this now. Here's a little cart that goes at a constant velocity. So that's the velocity relative to the table and you guys in your frame of reference. But what if this is like the wind on the airplane? If the wind's with you, do you see how the cart was actually going faster relative to you? Or the other way, of course. If it's a headwind. Yeah, we'll do that next. But here, if I can go the same speed as the cart, it doesn't even move with respect to you. Let's try that one more time. And then, yes. Yes. Well, actually, no, I can stand still because it's still, the wind's going across it. It can still be getting lift. It's like it's hovering. It's dumb because you're not getting anywhere, just wasting fuel. But it's kind of like a bee or a hummingbird that's hovering. If there's a wind blowing and it's going forward at the same speed, the wind's blowing against it, it just hovers. It's doing a lot of work and expending energy in a sense, physical, chemical work. But yeah, it doesn't go anywhere relative to the ground. So yeah, if you have the cross, and it's like what we've been talking about, or the typical thing is you got a boat trying to cross the river, but the river is moving. So you got the velocity of the boat and the velocity of the water. You know, if this is the case, this is the way I'll try to move it. Which way is the boat going to go? Diagonally. It's going to head that way, and it will never land right across the river. It'll land downstream. So like this. Now the component is, what's its speed relative to the ground? Well, if the water's not moving, that's its speed. If the boat's not moving and it just goes with the river, that's its speed. Put the two together and you have the diagonal relative to the ground. So it moves that way and that way. It's bigger than the two components. So like that. That's the same idea with these first two clicker questions. Does that help? Again, just for tying it all together, this one, we say it's shot, the projectile. You got a gun. It's the muzzle velocity. We say the velocity is that. The actual magnitude of its speed is that. We break it into components, though. We have an upward component and a horizontal component. And that determines how high up it's going to go and how far over it's going to go. That's good. I like that. So with relativity, it's frame of reference. This, it's kind of like what frame you're in. If you're in the cart, then you can see your speed relative to ground, the fixed frame of reference of the Earth. Those are the speeds we were just talking about. Let's do this one more time. This one, where you move with it. What's the speed of the car relative to the board? Very good. It's that speed. There's the relative motion. This moves relative to that. This just happens to be at rest. So the difference is easy to see. But try to watch the relative motion of the car with the board, even when the car or the board is moving. It's still the same relative motion between these two objects. This has relative motion with respect to the table. And so you add or subtract that to this guy's motion relative to the table to get his overall motion relative to the table. Your intuition's right here. And this works. That's how you add up velocities and whatnot, even when you're going faster and faster. It's just as you go closer to the speed of light, you can't add them up as simply. There's a formula in your book. I'm not going to ask you to calculate it, but the idea is like when you get to the ultimate, thought experiments. Einstein liked thought experiments. Take the extreme, and we did it. If you're going the speed of light, or you're on let's do it this way. You're on a spaceship going 50% the speed of light, half the speed of light, and you fire a torpedo, a photon torpedo, so it goes at the speed of light relative to you. So you're going half the speed of light, then you fire a photon torpedo at the speed of light. What is the Klingon ship over here that's at rest see, the speed of the photon torpedo? The speed of light. He doesn't see 1.5 times the speed of light. They don't add up equally because of this relativity thing. Point is, as you go faster and faster, you can't add them up or subtract them this simply. And there's a relatively simple formula in your book if you want to see exactly how to do it. And again, that formula will work at all speeds. Newton's laws only work at slow speeds. There's at the end of the chapter, it talks about the correspondence principle. It says, any new theory must agree with the old, when they're correct. That makes sense. I mean, we don't just make up new stuff that blows everything else out of the water, because why should this be wrong? I mean, unless we prove it wrong. So what that means is the equations of relativity correspond with those of Newton's laws. They both yield the same answer. It's just, again, Newton's laws only work at slow speeds. Theory of relativity works at all speeds, up to the speed of light. Maybe one of you guys will figure out a theory, because the theory of relativity only works up to the speed of light. It claims that nothing can go faster than the speed of light. What if someday we figure out that something can? We'll need a new theory. We'll have to adjust things. Does that mean the theory of relativity is debunked? No, it just means it only works up to the speed of light. We'll need something new beyond that, if that ever becomes the case. So that's the idea behind the correspondence principle in Chapter 5. So we got these two postulates. We talked about that no experiment can reveal absolute motion. No frame of reference is special over any other. All the laws of physics hold true in all these inertial reference frames. We get what we expect. We can calculate it. And the second postulate, speed of light's a constant. We all measure the same speed. Given that, we saw that, hey, that means space and time are interrelated. As we flow through space, that's how we should think of flowing through time. Instead of time just ticking past us, we're moving through it. And if one is adjusted, the other has to give. Because what's always the same? the speed of light. And that's a velocity, distance over time. So the ratio of space to time has to stay the same. That's consistent for everybody. So we saw that some events that happen at the same time in one frame of reference aren't necessarily happen at the same time in a different frame of reference. We'll disagree on that. We can also disagree on the amount of time it'll take for an event to happen. That's they differ by the Lorentz factor. We had if the time in your frame of reference here at rest, we measure something, we're at rest, like this guy's velocity. We say it takes so long to cover this distance. Well, now, though, if I take this on a spaceship going near the speed of light and do the same thing, what time will I get on the ship with it for the time it'll take to cross the board? One vote for the same. Who else thinks it'll be the same? Couple. Who thinks it'll be different? Most of you aren't playing. I'm in that frame of reference. So I'm at rest with respect to this event. So it's just like if I were back here with you guys and we're at rest with respect to the event. So I would still get the same time. Because I'm in that frame of reference moving with this stuff. We're all moving together. Well, yes. There you go. Now you guys staying here at rest, what do you guys get for the time it takes this to cross the board, looking at me on my spaceship? A different time, I'm hearing people mumble. And how much does it differ? That Lorentz factor amount. Whoops. You'll get a time that'll differ by the Lorentz factor. That's given in your book. We did it last time. It is 1 over the square root of 1 minus the ratio of the speed of light. So, if you're going half the speed of light, my spaceship, then that's, 0.5. You plug it in and you'll get the factor. And that'll tell you the difference in our times. Do you think the time will be faster or slower? The T.
Can you show us how you plug that in, though, with real numbers?
Yeah. Let's make it come out nice and easy. Of course, you guys have calculators. 87% the speed of light. Let's just start with that. That means 87%. Do you see how that would be the 87 right there? It's the ratio of your speed to the speed of light. If you're going 87%. Somebody plug that in. What do you get? What does gamma, the Lorentz factor, come out to be? Somebody do that. I know somebody's got a calculator. You square that, then you subtract it from 1, square root it, and invert it. That's how you would figure out this factor. .03? Thank you. So it's about a factor of 2. So there's one. The time will be a factor of 2. Now look at that. That means whatever time we got it to be at rest with it, let's say it takes, let's just see. 1001, 1002, 1003. So be it. 3 seconds. That's 3 seconds. Times the factor of gamma, which is 2. So t is 6 seconds. You will see, if I take this and do the same thing on a spaceship that's going 87% the speed of light relative to you, you will measure that time to be 6 seconds. See how it looks like time is slowed down? It's like it has more time to get from here to here, from your perspective, from your frame of reference. Me on the ship, I'll still get 3 seconds. 1001, 1002, 1003. It's moving relative to me. I mean, I'm in the same frame of reference, so we're all moving together. That's what I mean. Does that make sense?
Is that why, like, when you're on a plane and you go like far enough, like you can like gain an hour of time?
Oh, gain an hour of time when you're on a plane? No. That's the international date line with this whole time zone thing. So it's like just because you're going to a different time zone where they've set the time, said it's different. I mean, once you pass the international date line, depending on which way you go, you change a day. But it's just like crossing over a border and saying, oh, it's now 1:30 instead of 12:30. It has more to do with that. They've actually tested this, though, back before I was born. They took atomic clocks, really precise clocks, and they matched them up. They were identical, reading the same time. They put one on a jet and one left here at rest with respect to us, and then they flew that one around. When they came back together and compared them, what do you think they noticed? They're different. And they repeated this. They've done it in very different variations, and they've never been able to disprove this theory. It always seems to work. The clock that flew around was actually ticking. It was behind the one that was here, because it's like time slowed down for it relative to us staying at rest. And that works for biological clocks as well. If we, for that matter, oh, I should say, they were different, but we're talking like nanoseconds. It's a very small amount, not like an hour. This effect is small for such small speeds, because jet planes don't go near 87% the speed of light. Most things are less than 10% the speed of light. In general, scientists don't even worry about the theory of relativity unless you're going at least 10% the speed of light, because the effects are so small. So if you've ever heard somebody say, oh, that's relativistic, that means, oh, it must be going at least 10% the speed of light, roughly. But yeah, if you're going 87%, they'd differ by a factor of 2. So if the plane flew around from our perspective for 2 hours, 2 hours ticked off on our clock. How many hours ticked off from our perspective on that clock? 4. Differ by a factor of 2. It seemed like their time is slower. So hence, anybody go read about the twin paradox? It came up right at the end Friday. Anybody go read about it? Anybody read it in your chapter yet? Uh-oh. Well, the paradox. If you guys see my time running more slowly, but from my frame of reference on the spaceship, you look like you're moving relative to me. Because I'm at rest with my frame of reference, so it looks like you guys are going away at 87% the speed of light. So to me, it looks like your time slows down. To you, things look normal. To me, things look normal. But when we look at each other, we see each other's time as being ticking by more slowly. That makes sense, right? Who's right? You're both right. All right, so the paradox is you have these set of twins. One goes off on a spaceship for years, comes back, and when he gets out of the spaceship, the twin here on Earth has aged and is really old now. But the twin that went whizzing around on the spaceship near the speed of light is still young. Hasn't aged as much. They're different ages. How can that be if both people thought the other one was the younger one? That's the paradox. The bottom line is, who was actually accelerating? The one on the spaceship. So they both agree that the one on the spaceship will be younger when they get back together in the same reference frame. It has to do with, your book walks it through with some signals and everything to justify it for you. I just want you to realize that in order for the spaceship twin to get up to speed, slow down, turn around, speed back up, and then slow down to stop back on Earth, it keeps changing reference frames. They're not all inertial reference frames where the velocity is constant. Remember we talked about that. These are based on inertial reference frames. If you have a non-inertial reference frame where the velocity is changing, acceleration, that changes things. The general theory of relativity has more to do with that. But it's accounted for. Hewitt does a beautiful job in the chapter. I'll leave it to you to read. Just want you to realize that justifies the paradox. Because that person changed reference frames several times. But when they get back together, they both agree on the same answer. While they're apart, they disagree. You're younger. No, you think I'm younger. That's the paradox. But when we come back together, we'll both agree on who really did age less. Yeah?
Kind of thinking of space as like something that's actually moving like around us. We're moving through space in terms of it's not like they would. If you're thinking he's older, when they come back to the same reference frame in the same space, whereas one's different reference frame is different space, so it might be moving faster. Time.
That's a perfectly valid way to think about it. Yeah, it's this fabric of space-time. We usually just think of time, but we move through space also. And if you move through if time adjusts as we move through it, space adjusts also. They have to. So that leads to length contraction. If time adjusts by a factor of 2, if you're going 87% speed of light, so do distances, the space you travel. Example, in my spaceship, going 87% speed of light. What do I measure the length of my, no, we'll just have a meter stick. This isn't a meter, but it's close. The length of this, let's say it's a meter. What do I measure it to be? A meter. What do you measure it to be right now at rest? A meter. All right, I take it with me on my spaceship and go 87% the speed of light. I still get a meter. What do you guys get it to be at rest here on Earth? It'll be different. Good, you got that. It'll actually be less. Lengths contract. To you, with respect to me moving on the ship, my time seems to be ticking away more slowly. It's like I got more time to cover things. Another way to think of that is like, well, what if it was just because I had less distance to cover? So if one adjusts, the other has to adjust, is my point. So if time dilates, then lengths contract also. So again, to me, I can't emphasize enough, nothing's different to me on the spaceship with this. But if you were to measure distances on my spaceship, my meter stick, you'd get the meter stick to be shorter. It's as if, from your perspective, I have less distance that I have to cover. Technically, it's only in the direction you're traveling. So if relative to you, and I'm moving at 87% speed of light, then this will look half its length. But if I move perpendicular to you at 87% speed of light, there's no relative motion in this direction. Relative to you, you would still get this to be a meter if I move in this direction. But if I move right at you, the relative motion's in this direction, that's the way it's moving, at 87% speed of light, you would see this as half the length. Likewise, I would see your meter stick as half the length. The same paradox. But once I hop out of the spaceship and we're at rest with respect to each other, we'll both agree this is a meter. And again, both are right. And this is not just some perspective thing. You know how when you see something far away and it's moving, there's like some parallax, the angle. It's not just because, oh, that's the way you would say. It is that way in the different reference frames. That's why it makes this special theory of relativity pretty funky for some people. But it's all that Lorentz factor. So with length, it is, do it correctly so I don't say it wrong. Yeah. It's that. It's on the denominator there as opposed to the up above here, because time stretches out and gets longer, but the lengths get shorter. They have to keep that the same. So, but it's the same factor. If you're going 87% the speed of light, then the Lorentz factor is a 2. And the lengths differ by that factor of 2. Let's do some other ones. I find this interesting. If the Lorentz factor is 1, then you're not moving. It doesn't matter. 2 we did. That's 87%. 3, and this was just plugging numbers into that to see what V and gamma came out to be. 4, 97% the speed of light. So if you went 10% faster, you could change your time by a factor of 4. 5 was 98. 7.1 about is 99%. If you could go 99% the speed of light, you could time would slow down for that person by a factor of 7. Factor of 10 if you're going 99.5, and so on. Let's do like 70. That one's 99.99%. It's asymptotical in a sense. It kind of goes whoop if you plot versus velocity. And this asymptote is the speed of light. You can never approach the speed of light. I mean, you can never get there. You can approach it. But it takes more and more energy the faster you go. This works with momentum. What was momentum? Start our review now. Mass times velocity. Yeah. That's Newton's laws. That still holds. It's slow speeds. What if you're going fast? Then it is the Lorentz factor. And the faster and faster you go, you can see that the Lorentz factor gets bigger and bigger. It approaches infinity. So faster, 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 faster. Way bigger, way bigger. It's going to take an infinite amount of momentum to get to the speed of light. Thus, you can never get there, according to the special theory of relativity. Some of you might have heard that as you go faster and faster, your mass increases. Has anybody heard that? A few people. It's technically not quite that way. Classically, that's the way to think of it. In terms of Newton's laws, that's a way to think of it, and it's valid with that perspective. The faster you go, the more mass you have, the more inertia it is. Thus, it would be harder and harder to move you the faster you were going. It's really because of this. Because it would take an infinite amount of momentum the faster you go. That's a correct way to say it. So it's as if, with classical thinking, your inertia is just going crazy. Your resistance to change. This formula works too. E equals mc squared. It can factor as well with the energy. Einstein's most famous equation. What's it really mean? Yeah, energy is equal to mass by a certain factor, c squared. I like to think of it as energy is proportional to mass. They're like two sides of the same coin. And how are they exactly equal? By this factor, c squared. Don't think of that as a velocity. Because, speed of light squared, that's not a velocity. It's just, or you can think of it this way, E over m. That ratio is always c squared. It's a constant value. You can transform between energy and matter. They're like the same thing. They're just different forms of it. So here's some mass of the cart. Well, there's a bunch of energy binding all that all together. What if we could totally disintegrate this? Where would that energy go? Because total energy is conserved. It'd be released, go into the atmosphere. How much energy would we get? Yeah, whatever its mass is, times the factor c squared. You want to know how much energy is contained in holding this truck together? The molecules, the atoms, the protons, the neutrons, the nucleus, all that energy is bound up in its mass. If you could just disintegrate it, the energy doesn't disappear. That mass actually is converted into energy. And this would tell you exactly how much. Vice versa. You can take energy like gamma rays. There's like photons of light or whatever. And all of a sudden they can come together and matter can appear as they come together. Have you heard of antimatter? Or you watch Star Trek? Or if you have matter and antimatter and they collide, poof, it turns into a whole lot of energy. That's why it's a whole lot of energy. You take that little matter, but multiply it by a really big number squared, you're going to get a lot of energy out. You can also, a lot of that energy, spontaneously, we don't completely understand why, but all of a sudden you can get some particles formed out of nowhere. One of them's matter and one of them's antimatter. That is E equals mc squared. So to end, one last thought. I'll continue more Wednesday with the review. Space travel. Your book has a beautiful example about it. The nearest star outside of our solar system, anybody know what it is or how far away it is? Alpha Centauri. Do you know about how far away it is? It's about 4 light years. Light years is a unit of distance. It's how far light would travel in that amount of time. 4 light years. You can tell that's a really far, long ways away. So to us, at rest, in this frame of reference, we would think it would take 4 years to get there if we could travel the speed of light. If. Well, what if you're on that spaceship going the speed of light? Which you can't, but let's say you're really darn close. Well, to us here, it would look like their time slows down. So they got more time to get there. And when they come back, remember, they'll be younger than us. So to them, it won't take as long. Look at it the other way. If you're on the spaceship, things seem to be ticking away just fine, but for us looking at them, it looks like it's less distance. Because they're moving relative to us, so they have less distance to travel. Lengths contract. So to them, they don't have to go as far. They can get there in less time. So special theory relativity could make interstellar space travel possible. Because instead of taking 100 years to get there and we're dead, when you're moving at relativistic speeds, your time slows down and lengths contract. So it could make it possible. I'll give you an example from Ender's Game Wednesday when you guys come back.